Now in this lecture we shall learn how we can model, analyze and design a cold form steel structure as per the American standards. For American standards, there is an organization called AISI, that is American Iron Steel Institute. So that is the organization which provides us the design code for designing cold form steel structures. Now in this lecture we shall learn how we can model, analyze and design a steel platform structure like this. So first of all we go to a start software. Here I had already given units, meter and kilonewton and joint coordinates on the number 1 nodes as 0. Now we shall just copy paste this node by pressing Ctrl C Ctrl V option on our keyboard and pressing X as 3 meters. Similarly we press Ctrl C Ctrl V again and Z again as 3 meters. And by selecting all the joints here, in the Y direction we select the spacing as default spacing is 1.5 meter and link steps here. Now we need to add beams here. And after that, to distribute the loading here, we can add 2 nodes here. So we left click on insert node and add midpoint, go to geometry, add beam by perpendicular intersection. Now further we again divide this 3 meter into 0.75 meter spacing here. So after that we go to geometry, add beam by perpendicular intersection. Here we can add plan bracings also. So plan bracings act as medium to distribute the notional load that may be acting on this structure. And after that we go to specification here, beam, release my mz at starting and at end point also my and mz. So we select both bracings as well as secondary beams here. Here this is the end node, that is at the blue color. So we need to select end my mz and yes here. After that there is this one more approach that I want to teach you. That is basically sometimes it too happens that we don't want to transfer any movement from this upper platform to the lower columns here, as the cold form steel structures elements are very fragile elements. They are themselves very weak in both the planes, that is as well as along major axis as well as along the minor axis. So I don't want to transfer any bending moment from this platform to these columns. So what I can do is that I can release the bending moment on the top joint here. So we select all the columns here and select end and then assign. So here you can see that with this approach we can make sure that no bending moment shall be transferred from the beams to the columns here. And after that, to make the structure safe, or I should say laterally brace along both the directions here. So with this approach we can make sure that when a lateral force will come on the top joint, then the structure may not collapse under that on particular horizontal load. So we select both the bracings here and then again we can select assign them these releases here. Some people might be saying that they do assign truss to this particular element. So according to my perception, this start my mz and end my mz is far more practical as compared to the truss. So basically what will happen if you assign truss member here? So with this option, not even 0.01 kilonewton meter bending moment will be applied on this particular bracing here, but in reality it may be different. So considering all those things, my preference for bracing is always that always want to assign this start and end MYMZ to the bracings here. And if we want to assign the loadings also, so we can in this structure I shall only assign only the dead loads as well as only the live loads to make the thing simple. In the previous structure I had already teach you how we can assign the earthquake loadings and how we can assign the wind loadings. So just to give you a concept of how we can design steel structures, I am only assigning dead loads and live loads. So first of all we need to go to this option here, and we can name it as dead load. After that we can name it as live load. And to make things somewhat complicated, what I can do is that, let us say I want to assign wind load of some particular value. So I can assign WLX and WLZ here. So here we can go to this wind definition here. Let us say we want to assign a particular wind intensity. So let us say I want to check the structure for 1.5 kN per meter square. So left click on add here and left click on factor of 1. So here we can assign to view here, and after that we can go to dead load. We always need to add first of all the self weight here. To consider the connections weight, I can assign 5% here. So left click on assign to view and yes, and after that we can name the group here also. So we need to unselect the bracing sim member here as they don't transfer the loadings, and we can name it as group 1, select type as flow and left click on associate, and then we again go to this dead load and then we go to flow load group, and let us say the dead load over this structure is 100 kg per meter square, that is 1 kilonewton per meter square. So here we can see that now the loading is assigned. Let us check that whether this is a one-way panel or two-way panel. So here we can see that this is a perfect one-way panel. So we change it to one-way distribution and change it towards longer direction here. And after that, let us say our live load is in the range of, we need to go to flow load group 1, and let us say our live load is in the range of 200 kg per meter square. So we can assign -2 kN per meter square live load also. After that we need to assign wind load also. So here we can select it as open structure. So here we can see that some wind loading has been transferred. To see it more correctly, we need to go to labels, scales, apply immediately and decrease this value here. So basically the thing is that the loading value for this wind load is very less. So that is why it is not being amplified here. But after that we can again go to wind load along Z. Again we go to this wind load option here, and then we select Z and open structure. So similarly now the wind loading is being applied along the Z direction. After that we need to go to support. As the cold form steel structure member does not have any bending moment capacity on the bottom, so we need to assign pinned base at the bottom. So we can just select all the nodes at the bottom face. So with this approach, we can just do the modeling and the load load application for this type of particular structure. So after that we need left click on load case details, left click on add and auto load combination. Here we need to select AISI and the load combination category is public, and then left click on generate loads. So here you can see that these are the factored loads. So basically the AISI standard that is inbuilt into the STAT software uses LRFD load approach, that is load resistant factor design, not ASD or allowable stress design. So when we are designing this cold form steel structure, we don't need to apply allowable stress design load combinations, because in that particular manner your structure may be under designed. So to design the structures correctly, always go with load resistant factor design, and I will always recommend to repeat load cases and include notional loads. So left click on add here. So here we can see that all the loadings has been assigned. So all these are the generated load combinations as per the AISI LRFD. So to make the structure somewhat more complicated, what we can do is that we can just translationally repeat this whole structure along the x-axis. So we can select the default step spacing as 3 and number of steps as 2. So this is just a simple structure, but before that, to make the thing simple, what we can do is that we can also assign property to this particular small platform that we have made here. So left click on section database, and here we can see that there is a option called cold form steel. So under the cold form steel option, we have American cold form, Butler, British, Indian, Lesat, Kingspan, Robertson, Japanese, Australian, European, and Russian. So we shall, in this lecture, as we are designing with American standards, so we can select American cold form, and here there are two options, that is angle with lips and angles, channel with lips and channel, Z with lips and Z, hat, tube, and pipe. So all these sections I had already explained you in the previous lectures. That is, what is it basically the difference between angle and angle with lips, channel and channel with lips also. So in the next lecture, we shall learn how we can estimate or how we can assign the properties to this particular platform. So in this lecture, we shall learn how we can assign the properties to this particular cold form steel structure. So in the previous lecture, I had already explained you what are the different type of cold form structural steel sections that are available. So as we are doing with AISI, that is American Iron Steel Institute design, so I shall only prefer to give this American cold form steel sections itself. So for the columns, we can select channels. So when we left click on view table here, so here we can see that this number is basically the depth of that particular member in inches, and the B, that is here. So the width of the flange is written here. After that, the thickness of the flange is also written here, that is 0.07 inches, and this is the R value, and this is the moment of inertia along minor as well as along the major direction. So here we can see that along the major direction it is very strong, whereas along the minor direction it is very, very weak. So we shall always prefer that we shall only give the loading of the, or like the orientation of this steel structure along the major axis itself, as the minor axis or the weaker axis does not have any strength or moment of inertia. So similarly, for only one, as the height of this member is only 1.5 meter, so as per my judgment, we can take this particular member here. So left click on select here, and it also shows us the option that whether we want to go with front to front or single section from table. So left click on add here, and then assign all the columns as this particular member. And after that, when we want to assign the beam sections, so again go to section database and cold form steel. So here we can select again channels, and for channel we can, for beam particular section, we can go ahead with let us suppose we select this 5.5 cu 1.25 into 0.71. so left click on select here, and then left click on add here. So we can assign the main beam as this particular property, and after that, for the bracings as well as for this tertiary beams, we need to select another sections. So for bracings, we can select the angle as this 3 inches angle. So we can go ahead with this particular member here. Here also there is an option that whether we want to make a double angle arrangement also. So for the for the plan bracing, we can select this 3 LU 3 into 135, but whereas for the elevation bracing, we can go ahead with double angle arrangement also. So we can select this particular member here and star, and then left click on add here. So for the elevation bracing, we can select the star angle arrangement here, and then for the plan bracing, we can select this particular arrangement, that is single angle here. And for the tertiary members, we can select a very light section, as this is only 1.5 meter span. So we can go select this channel here as 3CU 1.25 into 7.1. So we need to select these particular members here and then left click on assign. So let us check that whether any property is missing or not. So all the members have been assigned a particular property, and after that, as we want to increase the span of this platform, so we can select X and default step spacing as 3, number of steps as 2. And after that, what we basically need to do is that we need to change the group definition. So let us check that whether the group definition has been changed or not. So here you can see that the group loading is only applied on this particular member here. So here we can see that as the scaling was not being initially changed, but now it has drastically increased. So with this arrangement, we can see that how wind force is being applied horizontally and vertically, along the Z direction. So after that, we basically need to change this group definition here. So we press Ctrl G option and then left click on highlight. So what we can do is that select beams parallel to X and select beams parallel to Z and then left click on associate. So with this simple option, we can change the group definition. So here we can see that and now the loading has been correctly applied, but we don't need to worry about this here, that the dead loading is not being applied on the whole structures. Sometimes it do happens. What we need is a simple refresh for the structure. So after that, when we will see whether the loading is correct or not, so here we can see that now the loading is correctly applied. And as we have not assigned any range to the wind load, so the loading is being applied on the whole structure here. So now our structure is ready for the next stage, that is analysis. So left click on add here and then we need to go to design and steel. So here we need to select this AISI standard. So this is the American Iron Steel Institute code that is being provided by the START software. And one thing, as I had already told you earlier also, that this code is dependent on the LRFD approach, that is load resistant factor design approach. So we left click on define parameters, and here we can assign this FYLD parameters, KT, KY, KZ, LY, LZ, ratio, stiff parameters, track and TSA. So let us say if we take the example of this blue scope light blue scope cold form structural steel. So here it is mentioned that blue scope layer sat cold form steel channels and angles are available either zinc coated or uncoated in base metal thickness of 1, 1.6, 2.5 and 3 mm depending on the section type. Now this is the important line, that the material used are zinc coated steel to AS 1397, that is Australian standards, G300, Z275, 300 MPa minimum yield stress and 275 G per meter square minimum average coating mass. So according to this particular specification, it is being mentioned that the coating on the this cold form steel shall be of 275 gram per meter square and the yield stress shall be minimum 300 MPa. So here we can see one more conclusion, that usually the cold rolled steel are is in the range of 275 MPa to 300 MPa minimum yield stress only. And if you are purchasing this material from the local supplier also, so it may happen that the strength of that particular local supplier's cold form steel may fall to even 230 MPa. So before designing, you do need a written specification from the vendor or from the contractor who is doing that particular work, that what exactly should be the yield strength that you should use in your design. So on an average, we can go ahead with 300 MPa minimum yield stress. Now coming back to start, so as it was asking about us the yield strength, so here we can enter 3, 1, 2, 3, 4, 5. So it is 3 lakh kN per meter square. So left click on add here, and after that we can enter these particular parameters also. So after that there is this lz command. So lz shall be 1.5 meter and 3 meter. So basically this yield strength need to be applied to the whole structure. This also needs to be applied to the whole structure. Now basically the thing was that this particular member and this particular member, this effective length along the major axis is 3 meters. So what we need to do here is that we need to select all the members in plan here, and then we need to select these members here. So these are the members on which we need to assign lz equal to 3 command. So left click on assign to selected beams and yes here. So after that we need to left click on commands, and here we need to select after current and check code, and after that we can also enter takeoff command. So left click on assign to view here, and then again assign to view here. So let us check that whether our structure is correct or not. So there are 11 warnings here that are being shown here. So the warning is applied self-weight is less than total weight of all the structure. So we don't need to worry about this particular warning here. We need to go to dead load. Here we can see the dead load is not applied to the whole structure. So these type of mistakes do happen when we replicate the structure. So here there are only 2 nodes and no errors and no warnings. So even then we need to see the output file here. So output file is not showing any particular error here, and after that we need to check the members here. So here we can see that first of all, as a advice from me, what we need to do here is that first of all always start from the smallest member, and then keep on checking its stability, and then move on to the next member, because there is no logic in checking the column when all the beams here are failing. So that is the the advice that my senior had gave me, and I am also giving this advice to you, that in the steel structure, as the number of elements are very large for steel, for 100 or 150 ton metric steel structures, your number of members may go up to in thousands also. So it may be very difficult for you to check each and every member. It may happen that you may pass this column and then again this beam may fail. So always start with this member and then go to this particular member, and then go to this member here, and then comes to the columns. So with this approach we can see that your all the things are being correctly entertained here. So first of all we need to check the orientation also. So the orientation of all these members are correct, but due to the fragile and behavior of the cold form steel structures, most of the members are failing. So first of all what we need to do here is that we need to pass this particular member here. So this is the 3Cu 1.25 into 71, and this is failing in bending along the major direction. So basically the capacity of the bending moment that is being coming here is 8.04 MPa. So we need to also enter the load list command. That command is also missing. So we need to enter load list, this 5 to 14. And after that, for this particular member we need to increase the size. So this was channel, and we need to increase the size 3Cu 1.25 into 71 to 4Cu 1.25 into 71. So left click on change here, and then we check that whether now this member is passed or not. So now we need to check. So here we can see that now the member is running on 87% utilization or 0.87 utilization. So that is an 85 to 90% is the ideal utilization. we need to go to from 0.9 to 0.95 when we know that the quality of construction on the site is very good. Otherwise, my tendency is also to stop myself at maximum 0.9 this utilization ratio, not more than that. And after that, we can see that this member is also failing severely. So the bending moment is very high. So here we can see that the bending moment that is coming on this particular member is in the range of 65, and this bracing is not taking much of the loading here. So this bracing is only working up to 7% utilization here. So that we will come afterwards, but now for this particular member here, we need to increase the size here. So what we can do is that the member size is this particular 5.5 cu. So we go to channel here, and then we can increase it to 8C 1.25 into 7.1 and double channel here. So left click on change here. So now we need to check that whether this member is passed or not. Still this member is failing here, that is 1.73, but it is like somewhat near to the target. So what we can do here is that we can increase to, let us check 10C 1.25 into 7.1 and double channel. So now also like we are just at the margin here. So these type of things do happen when you are designing steel structures. So we need to analyze again and again if you are not doing the manual calculation side by side. So let us go for the maximum size here, and somewhat desirable spacing also, and then again we analyze the structure. So here we can see that now this member is passing here, but let us check it whether this member is not passing or not. So here we can see that this member is not passing, but this member is passing here. So this member is running on this 0.78 utilization. This member is also passed. It is running out on approximately 0.79 utilization. That is, we have 21% reserve capacity here, but this member is failing here. So we need to do some brainstorming on how we can pass this particular member here. So there are various approaches, like when we are having this type of arrangement here. So what we can do is that right now we can check the remaining structure also. So this bracing is also getting passed here. This bracing is also passed here. It is also correct. And when we are talking about these particular bracings, then they are practically of no use here, because not much force is being transferred here. But when we go to select beams parallel by specification and all failed beams, we can see that these columns, the beams along the x-axis, and this particular bracing is failing here. So in the previous lecture we had already seen that this particular member and this particular bracing is getting failed in structural design. So besides that, all the members are getting passed here. So as an engineer, it's your responsibility that you need to find a solution that is economical also, and that solves the purpose also of getting an economical as well as safe structure here. So what we can do here is that we can delete the type of bracing here. Let me explain it to you. So basically I had deleted all the bracings here, and after that what we need to do here is that we need to add an additional bracings in the form of this shape. So here we can see that now we have formed inverted V bracing here. So here we can see that now the bracings are in a different manner. So the advantage of this particular bracing is that, let me tell you, first of all we need to assign the specifications here also. So the advantage of this bracing is that whatever loading shall come at this particular point, it does not need to travel to from this point to this point. It can get split it in two parts. That is, some part may go in this particular manner, and some part of the force may go in this particular manner. So we can assign a property also to this particular bracing here. So we can assign this 4 number property here, that is angle, and after that we can again go to this loading and definition to check that whether all the dead load has been considered or not. So we need to left click on assign to consider all the dead load here, and after that we need to again go to design steel, and we need to check that whether all the structures have been assigned this command or not. So now basically the thing is that LZ is not 3 for this particular member here. So basically this is the Z direction here, and the Z axis is getting broken after this 1.5 meter. So LZ is 3 is not valid for these members. So we need to select these particular members here, and then left click on toggle assign, and then assign. So with this approach we can make sure that LZ is equal to 3 command is only assigned to the beams parallel to the Z axis. And after that we need to take steel takeoff and check code command. And after that, when we analyze and design this structure here, so with this approach you can see that now this member is showing us very high amount of margin, that is it is only utilized up to 60% here. And when we check this column here also, here we can see that this column is also getting passed here. So initially this column was getting filled, but now basically the load is being transferred from this particular point directly to the supports here. So this bracing is also now passed, and after that when we check this particular member, here we can see that now the bracing is again getting failed. So what we can do is that let us check that whether this cross bracing will help or not, as the bracing we had initially applied only in this one particular direction, so that is why it was getting failed. So let us assign the specification to all these members here. And after that we need to check the again dead load. So here we can see that now the bracings are getting passed along both the directions here. So this bracing utilization is 94% and this bracing utilization is only 58%. Now if we go to select by specification and all failed beams, now we can see that all the beams are now getting passed here. So this was, as for my approach, is the best example that how you can pass the structure by changing the bracing here. What are the flexibilities that you have in a particular steel structures, and how we can economize and how we can take the maximum out of a particular steel structure arrangement for the economical as well as for the safest design here. So you have also learned how we can design the steel parameters as per the AISI standards, and what are basically the load combinations that we need to give for the load resistance factor design of cold form steel structures. And if you want to calculate the total weight of steel structures, we can go to results and steel takeoff. Here we can see that 5.229 kN is the total weight of the structure, and 10 kN is 1 ton. So basically this 5.2 kN is nothing but 0.522, approximately 0.55 metric ton or 550 kg. So the total weight of this particular steel structure is 550 kg. And if we want to check the deflections also, so to check the deflection we can go to post processing here. Now for deflection we need to go with the service load combinations itself. So we can assign a new like a load combination here. So we can name it as load 101 and name it as service, and this factor again as 0 and this factor again as 0. So now again we need to analyze the structure here. Now I am checking the deflection only for the this dead loads and live loads. So we can go to node displacement and summary here. So here we can see that under the case of this dead load plus live load, maximum deflection is at this particular point here, that is this joint, and this deflection is only 3.786 mm. And if we want to see that deflection for the limit load combinations also, we need to go to results, select load case, and here we can select all the load combinations here. And then when we go to summary here we can see that the maximum X displacement is 2.675. this is the deflection for the factored load. So I am telling you this just as a reference, but if you need to check the deflection, you need to check the deflection for the service load combinations, not LRFD or factored load combinations. So there's a big difference between both of them. So although the deflections are very nominal or very less in the factored load combinations itself, so we don't need to worry about the deflections or deflection criteria for this particular cold form steel structure platform here.